This presentation concerns the algebraic approach to the derivative. This is a topic in calculus. The standard approach in calculus uses limits. It turns out that algebra allows a different approach. There is some scope for new theory. However, the present presentation looks only at didactics. The presentation was held in Dutch at the Dutch Teachers of Mathematics Day, November 9, 2013. There was some discussion there, of course. The present discussion now here is in English without that discussion, but we will mention some of the conclusions. This is a summary of the presentation. Algebra allows a different didactics of the derivative. The didactics already has the standard notion of the procept, in which a mathematical concept can also be a process, or conversely. When we apply this notion of a procept to division itself, then there arises a distinction between normal division as a static concept and the new notion of a dynamic division with algebraic manipulation. A corollary is the new algebraic approach to the derivative. In this approach, limits are no longer needed to construct the derivative. Cauchy and Weierstrass remain relevant for university but are no longer needed for secondary education. Students can directly understand the algebraic approach. This allows easier transfer to courses in physics and economics. See the PDF of my book Conquest of the Plane at my website for more details. This presentation is divided in 8 sections. First, we shall look at the procept, which is the notion defined by Gray and Hall in 1994, which combines processes and concepts. A special kind of procept is the variable. This not only indicates a number, but also has a name so that we can use it in algebra. We shall look at the standard notion of division that uses limits. This standard notion shall be regarded as static, and then we introduce the new concept of dynamic division. A corollary of all this is the derivative that comes out naturally. The crux of this presentation lies in the definition of the dynamic division, and if you understand that, then we should have no problem in discussing the derivative. This is also a definition. The second question is, once we have that definition, how shall we teach it? My suggestion is then to continue teaching the derivative starting with surfaces or integrals. Once we have discussed this, we shall look at some of the problems in the current approach that are being solved by this new approach. We conclude by some questions to start up a discussion, but of course, as I said, those are not included in this presentation because the discussion was in Dutch. Before we start, I would like to mention some literature. There is the wonderful book by Boyer on the history of the calculus and its conceptual development. I can really recommend this because it's very insightful, both for the history and the concepts involved. There is also the Dutch book on teaching mathematics, and which has a chapter on calculus. There is the thesis by Gerhard Roorda on the transfer of mathematical knowledge to subjects like physics and economics. I have some criticism on these Dutch texts, but that is not relevant just now. And there's the website by David Hall, who introduced the procept. We see it here. And he also has been writing a new book, which probably is very good. Then there's my book, Conquest of the Plane, that contains the stuff of this presentation, and I can recommend it too. The PDF is available from the website. And perhaps I can mention that this approach to the derivative already was given in the other book, Logic of Exceptions, in 2007. So it just shows you what time it takes to present some new ideas. What we shall not be doing here is look at abstract algebra of the derivative. See the Wikipedia site, for example. There was also an approach by Jan Bergstra of Amsterdam on division by zero in a different approach. And if you look at some videos on the internet from the Khan Academy or from MIT, I find these videos somewhat saddening because they focus on the theory and they don't focus on the students. This is a personal opinion. Let me see what I mean. Let us see what I mean by that in the following presentation. The procept is a notion developed by Gray and Hall in 1994. You can find the original article on the website of David Hall, and it combines processes and outcomes. The best way to understand it is probably to start by an example. If we take the square root of 2, then we have two choices. We can grab the calculator and calculate it, or we can manipulate it as a symbol, like squaring it, and so on. It means that the symbol square root of 2 has two notions involved. The process, how it can be found, how it can be calculated, how it can be created, and also the outcome, a certain value, or perhaps even a certain mathematical concept. So we see here that the symbol has two kinds of meanings in which a very complex layer of connotations is involved. This is the elementary procept, an amalgam of three components: the process that produces an object and a symbol that is used to represent either process or object. And then Gray and Hall define the procept in general. That's a collection of these elementary procepts that have the same kind of object. Another example is that you have the verb versus noun distinction, to write versus a write, which means that the mathematical idea is also very common already in standard language. Another example taken from the Wikipedia is like 3 plus 4, that refers to a process of adding up, as well as the outcome of the process, which is 7. Now, you can use 3 plus 4, it's identical to 7, so you can use it to represent 7. You won't do that, but you might. The same addition for infinite sums, or here the definition of a function. It's the process of mapping x into an expression, as well as the outcome of that process, the function itself, that might also be represented by a line in a graph. Okay. Variable can also be seen as a procept, because we have a symbol that is x, where the x between quotes is the name. We drop it and we get the symbol. And we can choose a value, which is the process, and choosing gives us a chosen value, which is the ID, the result. And now there are two worlds that we have to take account of. There's the numerical world, where the variable x is always regarded as some kind of number. And this is also the conceptual world of the derivative according to Cauchy or Weierstrass. There's also the world of algebra, where the name x is turned into a symbol, and this symbol can be manipulated according to some rules. And the world of algebra is our conceptual world for this presentation. For example, if you want to eliminate the brackets in this expression, then you don't immediately think about numbers. You are supposed to apply some rules in which you manipulate the symbol. So that means that the variable can be used in different kinds of ways. Let us look at the standard notion of division and see how limits are used in there. The standard notion of division takes place in the conceptual world of numerics, and it causes a lot of work. For example, if we take a function that has been defined as a ratio or x squared minus 1 divided by x minus 1, then we see that when x is 1, then the denominator becomes 0, hence the whole expression is not defined when it happens. In the other case, we can factor this, and then we divide by x minus 1, and we have x plus 1 as the remainder, which can be done if x is not equal to 1, which is a very complex result of this functional expression. Now, of course, we can take the limit when x goes to 1, and of course then x will not be 1, but it's only approximate, or actually the limit value, and then we find expression 2. And we will say that a function is continuous in point A if and only if the limit there is the functional expression, the functional value at A. So when we combine these two, we can define a function g, which is associated to f, and has the same expression, provided that x is not equal to 1. And for the undefined part, we then plug in the limit value if x is 1. Of course, this is a complex expression. We can simplify this indeed to x plus 1 and then substitute x is 1, 2, and we can reduce this function in total to this expression. This example is only intended to show you how complex the reasoning has been. Also, the proposal is to get from vague to sharper use of language. Presently, when we say that a function f(x) is not defined when x is a, then we mean one of the following: either that x is a is in the domain of the function, so that only the value fa is not available in the range, or we might mean that x is a is not in the domain of f, or we might mean something confused, a combination of these two possibilities. That is the present vague use of language. And my proposal is to use a sharper definition. When we say that f(x) is not defined, we mean that x is a is not in the domain. That means that also the domain can be extended, and also that the range can be extended with the value of fa, which has the value of the limits for x going to a. We see this already in the derivative, because there the difference quotient, delta f divided by delta x, is not defined when delta x is 0. But we can extend domain with delta x is 0 and the range with the value of delta x going to 0, and we do that in the differential quotient. So we already apply this kind of process of extending the domain. This suggests a new definition of division. And we changed from numerics to algebra, and we introduced the explicit manipulation of the domain. What we have done before the division is now called static. So y divided by x is the numerator divided the denominator, remains like the above, and is not defined for when the denominator is 0. The new definition is dynamic division, and we call this y dynamic division by x, and will have the same outcome, y divided by x, unless we find that the denominator is symbolic. In that case, we assume that it's unequal to 0. We can simplify the expression, and then we declare the result valid for axis 0, 2, where we extend the domain. Now, we already have this notion by the expression simplify. In some computer algebra packages, this is already defined. We also have that the dynamic division is undefined when we plug in the numbers, because those are numbers. However, when we have a variable denominator, then we can x divided double x dynamically divided by x will be 1 for all real values of x. And very importantly, if we have a denominator x minus x, then it should be clear that this is not a variable, because it's a constant value 0, and it's very important to distinguish then the variable used in the denominator and the variable denominator itself. And the crux in this whole notion of the dynamic division is that there's a manipulation of the domain. When the domain of the denominator contains 0, then this is not considered during the process of simplification, but the domain becomes relevant again for the result. The derivative comes out naturally in the following manner. It can be defined by this program, where the delta f dynamically divided by delta x means that it is simplified, and then presumably delta x drops out from the expression in the denominator, and then we can choose it, set it to 0. And we can use the same notation as we have been using in calculus for ages. What happens is that first the domain of delta x is neglected at 0, which is the dynamic division. And in dynamic division, it's also extended with 0, but then we add the separate step of setting it at 0. Now, this definition must be distinguished from didactics with it. We shall spend more time below on the didactics. But the point is that a definition is not a problem, because it's just a definition. The didactic question is, why would we want to use this notion of derivative? But when we have some clarity on that, it turns out it's didactically simpler, because the whole issue does not rely on the notion of a limit. There is no limit expression here. And it also causes the question whether this approach does not allow for more attractive features. Now, it's easy to compare the three expressions. This is the standard differential quotient, and we clarify it by manipulations both in algebra, the simplification, and the domain when its domain is extended and then reduced to 0. And instead of using this order of notation, it's better to use this order, where you first simplify and then set the value at 0, which gives a more natural order of manipulation. Now note that in the standard development of the derivative, there is simplification as well. So if we take the difference quotient for x squared, then of course this is then the delta f, and this is the original function, and we expand this, we can subtract x squared, and then we can divide by delta x. So we already do the simplification in standard approach to the derivative, and we only write it down out in neater manner. There's a reader of my book who agrees then indeed Why would we resort to limits? And why don't we just simplify before we get close to 0? And then plug in, indeed, the value of delta x is 0. This manipulation of the domain in dynamic division also makes only explicit what already is being done implicitly. So this is the didactic advantage. And thus we conclude that the limit for delta x going to 0 into the differential quotient is equivalent to, well, simplified, extended domain, and then focus on delta x is 0. Now, please note some elements that the limit is not a process, but something in static predicate logic. So, for example, this is the original Weierstrass definition of the differential quotient. And you see that there are some properties that for every epsilon there larger than 0, there's a positive delta, such that when the delta x is in that range, then the differential quotient will be in that range. And this is not something that happens dynamically. It's a static predicate. And stories like it goes to 0 is only heuristical, and they create a conceptual world that's not necessarily relevant for the derivative. So it makes students think about all kinds of things, but not the things that are relevant for them. It's also vague here what it means that it is 0. When delta x is 0, it's not really expressed here what has the meaning of that, while in fact in the derivative we assume that delta x is 0. So it's a very confusing idea. Let me please note that also in the notation of a function, it's better to use square brackets than round brackets, because sometimes students multiply out. This becomes f times x times f plus f times delta x, and so on. So it's a small issue, but it's still something to be aware of. Now, in a presentation, this would be a moment to have some rest and have a discussion with the audience about whether these ideas are causing questions for clarification. And once we have had that small discussion, we can proceed with the next question, that when we have these definitions, how are we going to teach them to our students? Now, I presume that this discussion has been done, and I now continue with the discussion of how to teach it. So we assume that we have this new definition of the derivative, and now the question becomes, how shall we teach it? So what is a good way of didactics of calculus? Now, the standard approach now is to use the tangent, which of course relies upon division, and division is used to find the derivative. Instead, my proposal is to start with the surface or the integral, because this relies on multiplication, and this is easier than division. Also, it's related to division by means of the precept of the dynamic division. So when we start with surfaces and via multiplication come to division, then we can find the derivative, and once we have it, then we can start to explain tangents, which is the other way around, so not using tangents to explain the derivative, but helping derivatives to understand tangents. My book, Conquest of the Plane, thus starts with the surface. For example, if we take a constant function, fx is 0.8, we can plot it, and ask what is the surface between the horizontal value and the value of the function from x is 0 to x is an arbitrary value. In this case, we have selected 4, and we can multiply 4 times the height gives us 3.2. And we can, when we vary the value of x, then we can find a ray through the origin for the surface function. And indeed, when x is 4, we can find the surface at 3.2. Now, when we continue doing this, we can ask, for example, what's the surface under this function? And we see it's a triangle. So we multiply x times the height and divide it by 2, and we find a squared function, and so on. So building up surfaces from this function to that function, we can continue and find ever more increasing polynomials. It also is the case that when we have a surface function, we can go back and ask, what is the original function for which this is a surface function? Now, if we go into the more complex situation, this gives the abstract situation now, where we have a big F, capital F, which is the surface function for the area under a small f function for the value from 0 to x. And the question arises, what is the relationship between these? This will be the primitive and this will be the derivative. And if we want to know the change in the surface area, then we can estimate it as delta x times the fx, which is the estimate for this surface. And we can find the same surface here, which is the delta capital F, which is given as the standard expression between the new value minus the old value. And this gives the exact outcome of the surface function, and it can be approximated by this expression. And now the question arises, if we have a capital F surface function, what would be the underlying derivative function, smaller f function? And we can do that by dividing out delta x, and we can use the dynamic quotient to do that, to still have this approximate value. And of course, when we want to have a perfect exact value of this fx, then we want delta x to go to 0 and actually be 0, and we can do that by defining this expression. First we have this difference quotient, and then we set delta x to 0, and this gives us the derivative. And this process actually justifies the definition of the derivative. And we have no idea of a slope here yet. We have just the calculation of the surface and the relation between the surface function and the underlying derivative function. It's also interesting to see then that a function actually gives the rate of change of the surface under the function. We can see this when we look at the derivative and the slope of the absolute function, for example. Here we have the graph of the function. To the left of x is 0, the slope is -1. This is the big question, and to the right it is +1. Since these two slopes are different, it's pretty obvious that the slope at x is 0 is not defined. This is one possible line, but there are many others. However, if we use the new definition of the derivative, then we can take it as sine x in general. For example, at x is 0, if we write out the differential quotient with the dynamic division, and take the absolute value of x plus delta x minus the absolute value of 0, divided dynamically by delta x, then we find delta x, the absolute value, divided dynamically by delta x, and this we can simplify this into the sine function in general. And once we have simplified it, then we can set the value delta x to 0 and find indeed 0. Now this is a choice that you allow this simplification. It's kind of common in some circles to do that, and if my idea is to adopt that so that we get a difference between the derivative and the slope. Now the reasoning for the slope still remains the same, that the tangent here differs from there, so we don't have one there, but we don't need to say that we need limits on the left and limits on the right to have this kind of discussion. We can simplify the whole discussion that by saying that the derivative is something else than the slope, and you have to think about more clearly what the slope is to find it. One question is, what are the derivatives of the trigonometric functions? Conquest of the plane also has a suggestion for that approach. But we already are used to using x for the horizontal values and y for the vertical values. And it's suggested that on the unit circle with radius 1, to give values x, capital X and capital Y to all those points on that circle. That means that students already know that the capital X value gives us the X here, and capital Y value gives us the Y value here. And so we don't have to translate cos into X and sin into X. We already know X and Y, so there's no use to do very difficult about that. It's also suggested that we measure angles by the unit using the plane itself as the unit of measurement. Thus, for example, this is a full circle and it's also a full plane. A half turn, which is half a plane, a quarter turn, which is a right angle. And in this way, we use turns, and the nice thing is that we also find a circle in the middle with a circumference of value 1, and a radius then 1 divided by archy. Now, archy is written as capital theta, has the same value as 2 times pi. Now, we can understand that this is also a procept again, because you might want to use your calculator and calculate it, do the multiplication, but you also can understand it as a symbol and work with it as a single unit to prevent that kind of, to reduce that kind of confusion. I think it's useful to introduce the archy. And then we can divide the radius of this circle is 1 divided by archy, or this is the angular circle, then alpha multiplied by archy gives us the arc here. So I make a distinction between arcs and angles. And arcs are generally measured on the unit circle. Now clearly, basically alpha is also here an arc, and it's common to say that this is an angle of phi radians, but it's more clearer, I think, to use alphas as angles and phi for arcs on this circle. In that case, we get the trigonomic functions xr for alpha or x for phi gives us the cosinus of phi, and ur for alpha and y for phi gives us the sine of phi. This is a new kind of notation. It's intended to make it easier for students to understand where the trigonometric functions come from, and are various manipulations in the book to help understand all of this and to understand trigonometrics. The point remains that if we look at the derivative, then it turns out that those of cos and sine are very easy, and hence those don't change. Otherwise, if we would take the derivative of ur to alpha, then it turns out that it become arc high is the constant that turns up. So there's no simplification in terms of derivatives. Overall, the result of conquest of the plane is that it is possible to build up the secondary school program with the algebraic approach to derivative and to present deductions and proofs in a transparent manner. For calculus, namely, we have the integrals and derivatives of all the standard functions, namely polynomials, exponential functions, and recovered exponential functions, or logarithms. And we have the trigonometric functions, xor, tur, normally known as cos, sin, and tan, in different forms. And we find as well the rules for integration and differentiation, the definition of the exponential number, and we can also find partial derivatives, which are not in the program but should be in the program. Just to be aware that the book has also other results, but the main point is that the calculus program for high school is reproduced. What problems in the current approach are being solved by this new approach? I take an example from a textbook from 2006, where students in Dutch are supposed to find the derivative by means of a fully development of the differential quotient. And for example, for a times x squared, then they start out enthusiastically to write out the differential quotient and plug in the expression for the delta f and the delta x. Now, first steps, they still might write limit h goes to 0, but in subsequent steps, it often happens that students no longer write it like that, and this costs them points. So in a new approach, you don't have to do it like that. It's easier to write it in a different manner and still understand what you are doing. So limits are now regarded as essential for calculus, but they can be eliminated and regarded as confusing. So if we look at the Venn diagram with limits and derivatives, there is a intersection that is superfluous and confusing. Limits still are useful, but for different kinds of questions. Another issue is mathematical competence. It now develops slower than actually needed. From the book of Roda that I mentioned before, there is a list of issues from Thurston, and this list is supposed to be all kinds of angles of understanding the derivative. Now, if we have this new definition and infinitesimals fall out, and also the logical definition from Weierstrass falls out, and the other issues remain. So we have a somewhat more compact understanding of what the derivative is. Also, the relation to the slope is more sharp. Now, it's interesting to observe that David Toll, who developed the notion of procept that we have been using, has had no time yet, he writes me, to look at this approach, and he focuses on the use of the microscope to explain the function as a limit of what you get. When you put a function on the microscope and with ever higher and higher power, then it would, in the limit, approach to a line giving the slope. And that is his approach to try to explain the derivative. So it would be interesting when he would have time to look into the approach by means of the precept. There's also the issue of transfer from knowledge by students from the course in mathematics to other courses like physics and economics. And there's also the connecting didactics by teachers of those courses. Now, this has always been a problem, and elements in the explanation are that physics and economics don't quite use limits, so it's then difficult to link up if you insist on using limits. The course in mathematics is also slow in getting to the derivative because it's made more difficult. You need first to understand limits before you can start doing derivatives, and this can be simplified. Also, the math course focuses on change, difference quotient, slope, tangents, and stuff like that. And we have suggested that it is better to start with surface and see how the derivative follows from there. Another point is that in the didactics of mathematics, teachers have been oscillating between the Euclidean approach with axiomatics or realistic math, which is an approach to explain mathematics by issues from reality. And it would be better if they would, in teaching, focus on what students understand so that it becomes an empirical science. The following questions are suggested for discussion. The first one is, what is not clear in the above, or causes immediate questions? Secondly, is the approach already interesting enough for the training of teachers to alert them to the new didactics and the pitfalls in the current approach? Thirdly, is the approach already interesting for higher education where math is used other than for math majors? And fourthly, in the Dutch high school diploma for students that choose the exact direction, it's required that they know how to use the differential quotient to give a local linear approximation to a function. Now, when a student understands calculus via the approach in the above, it might not be too difficult to explain what the differential quotient is in the standard approach, in the classical approach. Now, is it possible to start up a process of change that the new approach is accepted in the field, where we have trials, where we adapt the textbooks, where teachers are trained, and then we might eventually reformulate the exam requirement? And why would we not do that? Now, we cannot have this discussion here, but in the discussion on November 9th in Dutch, we had the following cases came up. Student might get confused in a question like solve for x. Then it's tempting to divide by x because it would be allowed in the dynamic quotient. However, in this case, x is not a variable, but rather an unknown quantity. And you would assume either x is 0, then you can divide, or x is not 0, and then you can divide. And then this solves into x is minus 1. So there are two solutions, which can also be found by bringing all values to one side and then factor out so that you see the two roots. It's also possible to interpret solve for x as find the domain of x for which the equation is true, so that x indeed is a variable in the domain for the two solution values -1 and 0. In that case, we might uphold that x is a variable indeed, and then it still remains a matter of choice whether we can use the static division or dynamic division. Now, in general, however, we would see that dynamic division rather holds for proportions than for equations like the above. So this should solve one possible misunderstanding about the dynamic quotients. The second issue that came up in the discussion was that in Dutch high school for mathematics, the limits have actually already been eliminated. Indeed, in 2008, in the discussion of the change that was invoked, it was said that though limits are in a subdomain again, it is not intended to develop this into a very broad part. The limit is regarded as a necessary concept for the introduction of the derivative and for the study of asymptotic behavior of functions. But in practice, teachers speak about it vaguely, and for asymptotes, one tries specific numbers. Now, so for Dutch mathematics teachers, the argument in Conquest of the Plane that the limit for the derivative can be eliminated is superfluous. This may be so, but now the answer to this situation would be that limits are important and have apparently been removed for the wrong reasons and better be reintroduced for asymptotes, but the use of the dynamic division restores the lost exactness for the derivative in a transparent manner. So there is scope again for more exactness in the program for mathematics. So this concludes the presentation. I hope you take from it that the manipulation of the domain and of the algebra are key elements in the derivative, and that those key elements are captured much better in the approach via the dynamic quotients rather than limits. Please look at my website for the PDF of the book, and I hope you enjoy that. Thank you very much.